So Jaret, you are an engineer with MSL. What kind of engineer are you?
So my title on the Mars Science Lab is Mobility Systems Engineer. And what that means is I am on the team that have responsibility for all the parts of the rover involved with driving. So that includes the wheels, the steering actuators, the suspension system, as well as the software that helps keep us safe by avoiding obstacles, checking that we're not going to run off a cliff, etc.
There's a lot of new technology that went into the Mars Science Laboratory. Any into the system that you're working on?
Well, one of the great things about the fact that the Mars exploration rovers that we landed on Mars in 2004 was the fact that they lived so long. In fact, the Opportunity is still going today. The level of sophistication of the software that Spirit and Opportunity landed with was much less than it currently is. And that's because over the years of operations, we've been able to continue to write software, improve it, upload it to Mars, test it out on Mars, see it in operations. And so we've benefited from that kind of continuous development from MER. And yes, all that code made it into MSL.
Now, does the size of the rover have anything to do with the way that it moves on Mars? Because Spirit and Opportunity were, substantially smaller than the MSL.
Yeah. Well, it should, in general, improve our mobility performance. In particular, the size of rock that is of a concern to us is larger. Kind of rule of thumb is that the JPL style of rover that we build here is capable of driving over obstacles 1.5 times the wheel diameter. So in the case of MSL, the wheel is 0.5 meter, so 1.5 times is 75 centimeters. So that's a rock approximately that tall, yeah, that is safe for us to drive over. In general, we'll still try to avoid rocks that large, but that's a pretty sizable rock. And in principle, every one of the wheels could be on their own trajectory over an obstacle at the same time, and it would still be fine.
The style of rim, very sporty. What went into, designing a rim that was just like so cool?
Well, as you may have seen, there's kind of a hard tire that is machined out of aluminum, and it's black, and that's been what we call anodized, so the aluminum has been coated with a special treatment that makes it black. And that's primarily for reducing glint from the sun for our cameras, so we don't want to see reflections coming off the wheels in the camera view. And then the spokes inside the wheel are actually titanium springs.
Yeah, that's what I'm hitting right there, yeah.
Those are not really for driving, they're really more for the touchdown event, absorbing that impact on touchdown. Otherwise, they're really too stiff to be of much help while driving.
Now in the animation, the sky crane almost gets Curiosity to the surface, but Curiosity could actually be let go a little bit above the surface and drop down.
Yeah, we could suffer in general about a 0.5 meter free fall, and it's very unlikely that will happen. But you can imagine other scenarios where we are driving, maybe over a rock, and the rock rolls or what have you, or maybe we fall off a cliff with one wheel. Those springs will also help us in that event where one wheel smacks the ground after dropping about 0.5 meter.
But you probably won't be falling off of any cliffs because of the avoidance system. Can you tell me a little bit about the cameras that are on Curiosity that help you with maneuvering?
Sure. Well, we have a couple of different types of cameras. Mounted low to the ground, kind of on what we call the belly pan, both at the front and the back, are our hazard avoidance cameras. And those have big fisheye lenses that allow us to see a wide field of view, including the wheels themselves. And they allow us to image the terrain in front of us, and it's a feature of all of our camera systems that we use two side by side for what we call stereo vision. So it takes two-dimensional images from the cameras, builds up a three-dimensional map of the world, and can determine, hey, this obstacle is too big for me to drive over, I should choose a path that will take me around it. And then on the top deck of the rover, we have what's called a remote science mast, and on the top of that mast are what we call our navigation cameras. And these are spread farther apart from each other, still a pair, and that spread allows us to resolve things in 3D farther away. So that helps us to navigate over bigger distances, whereas the hazard cameras are kind of for the more immediate area around the rover.
But will it send back 3D images that, those of us here on Earth will be able to put on some glasses and actually see?
Yes, absolutely, yeah. So it will send back the two images that it used to build up the 3D map. And exactly as you put it, you can put on 3D glasses and and see Mars in 3D, and the public will be able to do that for sure.
So you're avoiding obstacles because you're trying to reach your science objective. And what you said to me a little earlier is that you're going to be doing a lot of driving. I think I heard a number of 135 meters per hour.
That's if you're continuously running the wheels. It's about like 5 centimeters a second. But in reality, we don't really travel that fast even, because the software requires us to drive what we call a step, which is usually about half a meter. Then we stop, we re-image the area, we crunch the data, make sure there's no hazards, and then proceed again. So
another half meter.
Exactly. Yeah. Yeah. If the terrain looks relatively benign, it will choose to skip steps and maybe skip 2 or 3 steps before it re-images again. But if you're in really rocky, undulating terrain, it will likely image every step, and that's where we go from 135 meters that we can drive in an hour if we're just going all out,
right,
to really only achieving about 150 meters a day, because we can't operate for 24 hours. We have to go to sleep at night and let the batteries recharge, and we have to do this stop and think maneuver as we're advancing.
Well, we wish you all the best with your mission and the engineering with MSL, and we look forward to hearing some follow-up stories about what's going on.
Thank you.
All right, thanks, Jaret.